In this video, we will learn the meaning of vapor pressure, how it relates to boiling point, and the factors that affect the vapor pressure of a liquid. Before we go any further, it's important to clear up something. The term vapor pressure, as in the vapor pressure of a liquid like water, has a specific meaning in chemistry. It is not necessarily the pressure of gas above a liquid or the pressure contribution of a particular gas above a liquid. This can be annoying and confusing, but listen on and we'll see what vapor pressure usually means to a chemist. Here's some water sitting in a beaker. If we heat it to the boiling point of water, which is 100 degrees Celsius, it will boil and bubble. If we heat it for long enough, all the water will boil. Now let's go back and take a closer look. Here we are at the water that's less than 100 degrees Celsius. Let's say it's at room temperature, 25 degrees Celsius. Zooming in, the surface of water is a complex rippling surface with water molecules moving all over the place, but we're going to keep it simple and draw a straight blue line. Above the water, we have air, which is about 1,000 times less dense than the water. In air, we have various gases, nitrogen, oxygen, argon, carbon dioxide and so on. But even at 25 degrees, we don't just have water in the water, we have water vapor in the air. Liquids do evaporate even below their boiling point. Puddles don't boil after all, but they still disappear eventually in the heat of the sun. Vapor pressure is a measure that helps us understand what goes on between water at room temperature and water boiling. But to understand this a little better, we're going to need a more controlled environment. If we have water open to the air, our pressure meter will measure atmospheric pressure. As the water warms up and more water evaporates, the pressure meter will always read 1 atmosphere. That's because we're in an open system. The pressure of the whole atmosphere isn't going to be affected by us boiling a little water in the lab. Instead, we need a closed system so we can study what's going on. Let's put the beaker in an airtight, pressure-resistant box and heat the water up like we did before. Now, when we warm the water, we see the pressure rise. However, something odd happens. The water isn't boiling even though it's at 100 degrees Celsius. And it's not boiling at 105 degrees or 110 degrees. We keep heating, and at 120 degrees Celsius, the water finally bubbles and boils. We know that water boils at 100 degrees Celsius when the external pressure is 1 atmosphere. But the pressure inside the box now reads 2 atmospheres. By boiling the water, we've vastly increased the pressure inside the box. We now have a controlled environment where we can measure the pressure, but the behaviour is very different. So how do we make sure that the water inside the box boils at 100 degrees Celsius? All that air at the start is what's providing the extra pressure, so let's remove it at the start with a vacuum pump. We now have our box with only water in it. There's liquid water in the beaker and there's gaseous water filling the rest of the box. Now let's do the heating again. At 25 degrees, we see a pressure that's almost zero, 0.02 atmospheres. At 50 degrees Celsius, the system stabilizes at about 1/10 of an atmosphere. And the pressure inside the box is about half an atmosphere, around 80 degrees Celsius. And as we reach 100 degrees Celsius and a pressure of 1 atmosphere, the water boils. If we continue to heat above 100 degrees, the water will eventually boil away, but it does depend on the size of the container. All we were interested in finding was the boiling point, 100 degrees Celsius. Now we have a way of measuring the pressure of the vapor of a substance at a specific temperature. We can look at vapor pressure. Vapor pressure is the pressure exerted by a gas in dynamic equilibrium with its liquid state in a closed system in the absence of other substances like air. We can see the meaning of the term dynamic equilibrium if we take a closer look. Water molecules will be evaporating from the surface of the liquid into the gas phase. They're evaporating. But at the same time, water molecules in the gas phase will be hitting the surface of the liquid and condensing. To be in dynamic equilibrium, the rate of evaporation must equal the rate of condensation. This is another way of saying we measure vapor pressure when the system has stabilized. And the last thing is that the vapor pressure of a substance is a measured quantity at a specific temperature. Now let's have a look at the relationship between the vapor pressure of a substance and its boiling point. When we refer to a substance's boiling point, we generally assume that the pressure is 1 atmosphere, since that's the condition we're used to. So we can define boiling point simply as the temperature at which the vapor pressure of a substance is 1 atmosphere. But there's a general definition of a boiling point which is dependent on the external pressure, whether it's 1 atmosphere or something else. We can use the relationship between boiling point and vapor pressure to predict the behavior of liquids at other temperatures. We know the boiling point of water is 100 degrees Celsius, so the vapor pressure of water at 100 degrees Celsius must be 1 atmosphere. At temperatures below 100 degrees Celsius, the vapor pressure of water is less than 1 atmosphere. But what does the curve look like for a substance with a lower boiling point, like ethanol, with a boiling point of 78.4 degrees Celsius? Wherever we look, the vapor pressure for ethanol as a liquid versus water as a liquid is higher. Ethanol, having a lower boiling point, is more volatile. When doing comparisons, we need to make sure we're doing things at the same temperature. This principle holds when we're dealing with two different liquids. When dealing with solids and liquids, it's a bit more complicated. So far, we've only considered the vapor pressure of pure substances like water. What if we have a solution? A solution still has a vapor pressure. We can place a solution in our box, remove the air, and measure the pressure of the gas after the system has stabilized. If we add salt to water, will the vapor pressure go up or down? When we add sodium chloride, we form sodium and chloride ions, but water can still evaporate. However, the rate of condensation will be greater than the rate of evaporation. So we see a reduced vapor pressure and an increased boiling point relative to pure water. And the graph of the vapor pressure against temperature will look something like this. We can think of the sodium ions and chloride ions as reducing the surface area available for water to evaporate, slowing the rate of evaporation. This reduction in the vapor pressure of a solution relative to the pure solvent is an example of what we call a colligative property. The reduction of the vapor pressure is mostly dependent on the number of dissolved particles and not on the identity of the particles. What's also interesting is that adding salt to water reduces its melting point as well as increasing its boiling point. Next, we're going to move away from the box and look at real ways of measuring vapor pressure. There are many ways of measuring the vapor pressure of a substance, but one of the most simple is called a manometer. A manometer is most useful when the vapor pressure of a substance is relatively high. There are two main types of manometer, but we're only going to look at one type, the open-ended manometer. The key part of a manometer is a U-shaped tube, usually made of glass. Inside the glass, there'll be some liquid. It helps if the liquid is very dense and has a very low vapor pressure itself. This is why liquid mercury is very commonly used. One end of the manometer is left open to the air, so the pressure on that end is always 1 atmosphere. The other end can be connected to our flask. In the flask we put our pure testing substance and make sure there's no air. When the system stabilizes, the vapor pressure of the substance in the flask will be competing against atmospheric pressure, pushing the mercury up or down. If at the given temperature the vapor pressure of our substance is greater than 1 atmosphere, the pressure on the left-hand side will be greater than the pressure on the right, so the mercury will rise on the right and fall on the left. But if the vapor pressure is less than 1 atmosphere, then the mercury will be higher on the left than the right, because atmospheric pressure will be greater than the vapor pressure. The difference in height of the two columns combined with the density of mercury gives us a measure of the pressure, but we won't be looking into that calculation in this video. What's important to realise is that the greater the vapour pressure, the lower the level on the left-hand side and the greater the level on the right-hand side. Now it's time to do some practice questions. The image below shows 3 manometers, each containing a sample of ethanoic acid. For which manometer is the temperature of the ethanoic acid the highest? We can use manometers to measure the vapour pressure of pure substances. In all the manometers we have exactly the same amount of ethanoic acid. Above the liquid and in the tubing we're going to have gaseous ethanoic acid. The other part of the manometer is the U-shaped tube that contains a dense liquid. Here I'm assuming that it's mercury. If we heat the ethanoic acid in the flask, we're going to increase the amount of ethanoic vapour in the tubing. This is going to increase the pressure on this side of the manometer. This vapour pressure is going to compete with the external pressure applied to the other side of the U-shaped tube. We can assume it's 1 atmosphere. The most important thing is that it's consistent between A, B and C. The question's asking for which manometer is the temperature of the ethanoic acid the highest. We can label the temperatures TA, TB and TC. The lower the level of the mercury on the side of the flask, the higher the vapour pressure in the flask. We can put the manometers in order of the height of the mercury on the side of the flask. The height is greatest for A and lowest for C. This means the pressure inside C must be the highest of the 3, and the temperature of the ethanoic acid in C is greater than the ethanoic acid in B or the ethanoic acid in A. Therefore, the manometer in which the temperature of the ethanoic acid is the highest is C. Let's finish off with the key points. The vapour pressure of a substance is the pressure of the gas that is achieved when we establish dynamic equilibrium with the liquid substance in a closed system in the absence of other substances at a given temperature. The boiling point of a substance is the temperature at which its vapour pressure is equal to the external pressure. More volatile substances, which are substances with higher vapour pressures at a given temperature, will have lower boiling points. And adding solutes to solvents like water lowers the vapour pressure, raises the boiling point, and lowers the melting point.